Today we are going to create a battery cutoff circuit, which is a charging cutoff, and we are connected a relay to control the battery, and we have this circuit to input the analog voltages which goes to the A0 pin. We also attach a bunch of push buttons to control the settings, and we attached the LCD 16 by 2. And first of all, let's create a Proteus simulations. So we are going to use an Arduino UNO to simulate our circuit, and here we have 16 by 2 LCD. First of all, we have to make sure what pin goes to which Arduino pin. So because we have our circuit diagram, and we need to figure out which ATmega 328P pin goes to which Arduino UNO mapping. So we need to find out Arduino digital mapping, and here we have the pin configurations. So let's check out the 4 pin is RS, and RS goes to 11th pin, and the 11th pin of the ATmega 328 is a digital pin 5 of the Arduino UNO. So we need to connect the RS to the 5 pin of here we go. So here we have our RS. So we'll map all of these pins similarly. So we have pin number 6 for the enable, which is the 12th pin, and up to so on. So next thing is 11th, which is connected to the 13th pin, and the 13th pin is 7. So, and the 11th pin of the LCD is the D4. So we have D4 here, and we can go to the same direction. Here we connect the enable pin. Here we'll go with the D4, and then we need to connect rest of the pins, so which is D5, 6 and 7. We'll connect them to D8, D9 and D10 of the Arduino UNO. Now that we connected all of these LCD mapping, we are good to test our liquid crystal interfacing in our Arduino software. So let's begin with a new sketch. Here we need to interface the LCD, so we'll open up the examples from the examples directory, and we need to find out the liquid crystal, and we can fetch any of these. So here is the way to connect the LCD. We already use this configuration, so it lists from this way. So let's grab it, and we copy that, and we'll simply paste it into our sketch. So this is what we're gonna do. And for the RS pin, we know that we connected the RS to our D5. So let's go back to our sketch and change this pin. So make it 5, enable is 6, then 7, 8, 9 and 10. So once we're done with our pin mappings, we can come back to our example and initialize the LCD in this manner. And after that, we can copy this loop as well into our loop. Let's name this AM battery controller, and I'm giving this some code names. Okay, so now we have this. We'll just simply create a hex file for that for our Arduino UNO, and it will start building, and we need that hex file so that we can load that onto our simulations. We'll wait for this compilation to be complete. Now that our compilation is done, we have the path for our ELF or hex file. We can load this file into our in, and we can select the hex file here or ELF, whatever you can use. I'll go with the hex file, and all the remaining configuration would remain the same, and these are the fuse configurations if you are concerned to change them. I'll leave them as it is for now, and let's test if our LCD works as expected. So yeah, hello world is being displayed, and in the second line the seconds are being displayed. So that's for the LCD initialization. We'll go with the A0 to read the analog value, and here we have the A0 channel. We'll get that readings from some potentiometers, and we'll display that onto the LCD. So let's get back to our sketch. We'll close that. Here we'll change the first line to the lcd.print cv, and we have 0, 1, 2, 3, and from the fourth character we'll write the readings of analog channel. So we'll change that analog dot read A0, so it will display, and will again come to this after 1 second. So the readings would be after every second. So we'll save that and recompile the code so that we can run on our simulation to verify that it is reading the ADC channel. Our compilation is done, and we are good to test what it is. Oh, okay, so it is displaying this on second line, but we need that onto the first line. So we'll just simply change a little this from 1 to 0. So for that reason we'll switch back to the first line here. Once the compilation is done, we can test that it goes back to this one. So for the A0 we need to add another component, which is 10K port, and into the resistors we need the active part, the potentiometers. So if we write a simply port, and we'll get this active component, and we need this active component, so we can change the potentiometer's value. So we'll simply grab this one onto the surface, and we'll attach this one to A0 to simulate our voltages, and we are simply getting from positive 5 volts to 0 volts, and will map this reading from 0 to 1023 value. So basically the ADC is 10 bit, which is 2 raised to power 10 is 1024, and -1 is 1023. So the maximum value the ADC will return on the full scale would be 1023, and because the potentiometer is halfway set by default, it is giving 512, which is exactly the half of the full scale. So if we increase this potentiometer we'll see that a rapid increment in the current value of the ADC. Uh, because we don't want that numbers, we need the reading to precisely scale from 0 to 100. We can simply change this value from 0 to 1, 0 to 3, up to the 0 to 100. So how we can achieve that? Gladly, the Arduino comes with a built-in function which is a map function, which can map any readings from any ranges up to any ranges. So we can simply use our variable, which is int ADC val is equal to 0, and we can go down here. Let's first of all grab some reading. ADC val is equal to analog read. This is a raw analog reading. We can also create ADC channel, and this could be A0, and we can pass this parameter. So now we have the ADC value, and we can create another variable which is current value and is equal to 0, and we can simply say that current value is equal to map, and which value to map, and what range it currently holds, and what range we want from that. And once we're done with that, we can display this current value to our LCD. So rather than just simply putting the raw analog reading, we are now printing the mapped value of the ADC reading. If we recompile the code, we are good to test on our simulator. Our code is compiled. Let's test that into the simulator. Now the current value is 70, and if we make it full scale, go to the full, and we'll see that we have the 100 reading here. And if we come back down, we'll see the decrement in the reading, but here you will see one simple change. So here we have 3 zeros. So what happening here is basically once we print the 3-digit value, it come back to the 2-digit, the remaining 3rd digit will remain the same. So if I increment the potentiometer value, instead of displaying the 30, it is being displayed 300. It is not the actual value, so basically what is happening, it is printing the 3-digit value. So how you can handle these conditions? You can manually print the 3 digits onto the LCD. How you can do that? We can simply create a function. I call it display 3D or 3 digits and int value, and inside that what I'm going to do is lcd.print, and here I can say, first of all, let's print out the 3rd digit, modulus 10. So this is the 3rd digit here. Now we can repeat this process with 10 and simply the modulus. So that would be the way to print a 3-digit value with the leading 0. This is a one way to do that. We can definitely use as printf function to build a string, then display that, but I'll stick with the simple solution. This could be a mathematical hungry, but the computation costly, but I'll stick with that for now. And instead of calling the LCD print here, I'll call this and current value. So this will solve the problem, hopefully. This might not be the optimum solution, but it will do our thing. So I'll go with that. I'll wait for this compilation to be done so I can test. Okay, so we have a syntax error. We need one more parenthesis here, I guess, maybe. So we have this one, then we are closing this one, then we are closing this one. So we have the multiple parentheses included, so we need to cover. Compilation is done. Let's get back to our simulator to see what is going on. Okay, now it is displaying 030. So cool. I'll simply get that up to 100. Once it's 100, I can make it down to 0, and then simply somewhere in between 20 and 30, 40. Okay, so the display is correct. Now we have this value. What if we want to make it a 3-digit value? So instead of handling the floating point, what I'm going to do is, instead of mapping it to 0 to 100, what if I map it to 0 to 1000? So what it will do, rather than 1000, let's make it 999. So it will keep a 3-digit value. So what if you are displaying this onto a 7-segment 3-digit 7-segment value? So you can use the same code. So now I'll map 0 to 3-digit value, and here what I'm simply going to do is lcd.print a simple dot. So what it will do, it will display the reading from 0 to 99.9. So it will give a visual effect of a point value. So I'm not dealing a floating point value, but yes, I'm dealing with a integer value and simulating it as a floating point value. So now if you see, it is 40.0 rather than 400 or a simple 40. So what if I change the value? Now you can see that it is jumping from some states. So now you can not take a linear effect of the readings to display. For example, one step down, it is giving you the 59.9. So the smooth transition is not possible because you interpolate the values and your variable is jumping because it is not giving the linear reading, so you are not able to see the linear reading here as well. Let me grab this one and make it closer to the LCD so we can do the things together in one screen. So now I have a potentiometer and this LCD. So if I increment, you see 59.9, I press up one time and it will go from 59.9 to 70, and if I decrement, it goes back, and from 59.9 it goes to 49.9, and from that it is going to 40. So as you understand, the transitions from the states are not linear, and it have jumping, which you will see in a real time, and we can cover that with an exponentially moving average filter, which I put a video on my YouTube channel. I'll give that link to how to smooth this reading with the exponential moving average filter. I explained everything, how that filter helps to go smooth out the ADC reading. I'll leave that link in the description or the iCard. You can check both, and we'll move forward to our coding from this, and we'll create one more value, which is a set value. So what we are going to do next is to provide a set value which when met, the relay would be turned off, and when we press a reset button, the charging will start again. So we'll have one reset button. When pressed, it will go back to when we press a reset button, it will turn off the relay, and the charging is started. So when the set value is met, the relay is off or on. We'll manage that state, on or off. We have three buttons to make our set value, so we'll go back into our coding to make the settings available. We attach the two buttons with the set up and set down, and we interface that to the digital pin 2 and 3, which is exactly attached to the 4 and 5th pin of the 8MEGA328 microcontroller. And because we had attached buttons in our circuit in the actual hardware, which looks like this. So this is our PCB board that we are working on, and we need to display the readings on the LCD of the set value. So we created another variable, and we call that variable the set value, and we are going to display the set value in a similar manner. And first of all, we'll lcd.setCursor, and we are going to the 4 and 3 is 7, and 7, let's start from the 9 and 0, and we'll lcd.print and sv colon space, and after that we are going to display the 3-digit value of the set value, right? So if now we compile and check, we need to create two buttons as well. So let's define buttons from 2 and 3 pin and make these pins as SW up, input, pull up, although we added the pull-ups in our hardware as well, but just in case if we don't. So we have these two buttons. Now what we need to do is if okay, so we'll copy that and shift this into our setup, and let's grab these variables and put them up here, and let's grab this macro and put that here. So now we have these values, and what if we make separate function, void display set value, and inside that function we put this one here, and we simply call this function in our setup. So now we are good to go. Let's add if statement. If digital read SW up is equal to low, then delay 100 millisecond, and while digital read SW up is equal to low, what we're gonna do, set value plus plus. If set value is greater than 999, we are going to make it 0 and then display the set value. And once we're done with that, we will take a 200 or 300 millisecond delay and we are good to go. Let's grab this one and duplicate, and this time instead of up we are going to do with the down button, and we'll decrement this value here, and if it's less than 0 we'll make it 999. So this way we are good to make our up and down settings for our set value. And one last check we can make is we can create a simple relay, and which pin we are using for the relay. Let's take a look into this. Is pin number 18, and pin number 18 is digital pin 12. So that's digital pin number 12, so we are going to use that pin for our relay, and we'll make this relay pin mode output, and okay, so the relay will be on with the logic high, so by default we'll write the relay with the low. Okay, so now we'll make a simple check here. If the current value, this one, if current value is greater than set value, we'll need to turn the relay off. Okay, so we'll make sure that digital write relay, and relay will be off, and we will need to make sure we'll read another button, SW reset, and this reset button is attached with the pin, let's say we'll use 6, pin number 6, and the pin number 6 is digital 4, so let's use this pin D4. So we'll make this pin mod SW reset input, so we'll use this one, and if digital read SW reset is equal to low, all we need to do is turn on the relay again. So cool. And if we, before leaving the setup, we'll check if current, okay, so we can't make this one, and let's say make a delay a little bit, and then relay high. Cool. So now we have relay high and we have set up our logic. Let's recompile and test. So think for a while. What we are going to do, we just added the increment and decrement to set our set value, and we make a reset button, so whenever pressed it will turn the relay on again, and if the current value is greater than set value we'll have to add equal to here as well, so the set value will match. So whenever the set value is matched, the relay will goes back off. So we are good to add another button in our simulation. So we can simply use one pull-up resistor, one more here, and we need a button which will be a reset button, and we'll make this ground and we'll use one more pin like here, and this will be SW reset, and we'll add this one to this. So let's make sure that our label is correctly added. SW reset. So now we have that, and here we have one more, which is relay. So we'll simply call this relay. And how to make a relay, we'll grab one LED for now, and from the optoelectronics inside this category we'll make an active LED. Edit, this is a bicolor LED, we don't need that bicolor LED. We'll simply grab this one or any green LED. Okay, so and we need 100 ohm resistor. From the resistors we can simply grab this 100 ohm resistor, and we'll simply add here, and then we'll add a LED, because the LED is going to be turned on with positive. So we'll just simply put this one into negative, and we'll add this one label here, and we'll call this relay. So now we have everything set up. We can hopefully run our code. Okay, so the set value is not properly being displayed on the screen. We need to make a little tweak to our code, and we will go back, and we'll simply, what we do, we simply reposition the set value from 9 to 8. So we'll recompile that code, and let's make this one. So let's wait for the code to be compiled. Our code is compiled. Let's test this one onto the simulator, and we have this current value, then we have the set value. Now both of these are being overlapped. So let's not put the where we are putting this one. Instead of 4, let's make it 3, and instead of putting a space, let's make it back and put a comma. And let's see if this is going to be adjusted in one line. I know I can utilize a second line as well, but that's not my intention for now. Let's use this. Okay, so now we have the current value and the set value. We can up. No, yes, we can. We need to keep it pressed, and so it will be incremented. One more thing I need to look here is that because the set value is less and current value is greater, why not it is just turning this on. Let me check the logic. Here is 0 and the relay is 0, which shouldn't be the case. Let's see what's wrong here. If the current value and if the reset is low, it is going to put it high, and yes, because the set value is greater, it makes it low. Yes, it will make it low, and it will only be turned on if I press this reset button. So when I press this button, it should put a high, but with the same line check, this one goes back. So I need to make my current value a little bit lower. So now we have 9.9, and now if we press the reset button, it's still not the case. Yes, the LED is turned on. So when the value goes above the set value, LED goes off again. And if I make it down like this, current value, now current value is 20 and this is 21, I need to press a reset button, then release it, and it has to match. Yes, because this is a simulation and this is not real time, it is being slowed down, and that's why the LED is not being lit up first time. So the simulation is not running in real time, this error, due to excessive CPU load. That's why the Proteus is not a good simulator, but it will check your basic logic. So I think that's all for today's tutorial. Hope you enjoyed. If you have any question, just leave a comment below. Thank you.